Section 1.7 will conclude our chapter 1 of our book. We have had linear equations, quadratic equations, and then we had that last section which was miscellaneous equations, which included some things that were quadratic-like, some things that were radicals, and some absolute values. In this section, we're kind of going back to what we did with linear equations in section 1.4, but we're not doing equations any longer, we're doing inequalities. So I want to start with a little bit of a discussion about inequalities. So inequalities talks about how things are not equal to one another. So one of the inequalities that you could actually do is to set something to say this does not equal this, right? Like we had at the very end of that problem that Elijah told us something's not right, right? 3 is not equal to -7. It's not equal. So that's actually an inequality, but it's not an inequality that gives us as much information as the ones we usually work with. We usually work with inequalities that talk about which one's bigger than the other one, a comparison of them, not just that they're not equal, but which one's larger. So our two that we typically see, and then there's variations of them, are less than and greater than. And the variations are less than or equal to, greater than or equal to. So that's what we're going to start at the beginning here, is to talk about different ways of representing those and how to move between those representations. So we have 3 separate representations of how to understand or think about solutions for inequalities. One of those is the set notation. A second one is an interval notation. And the third one is a graph. So it's a graphical notation. A lot of the directions that we work with say simply to solve and give a graph. They don't necessarily say you have to give an interval. But I want to show you how to do that so that when they do ask you to give an interval as well, you're prepared to do so. So the first thing we're going to work with is we're going to work with changing from set to interval and graphical notations. And I'm going to do that by starting with the set and creating a graph, and then I'm going to go back to create the interval so that you can see the relationship. So over here on our graph, we're going to draw a number line, like so. Number lines have arrows on the end. And the value that matters from the set notation at the beginning is the value A. So we're going to put an A on the graph. For the most part, if we're given a single value, it doesn't matter what that value is in terms of is it positive or negative, where does 0 lie, do I need to put hash marks out or anything? You don't. You just need to put that value on the number line. If it's 5, you put the 5 there. If it's a -52, you put -52 there. Now, what we do need to pay attention to is we need to pay attention to the fact that this tells us that x is greater than a. So if you think about the a where I placed it on the graph, is greater than to the right or is greater than to the left? It's to the right. So you will do some sort of shading, emboldening, change the color, something to indicate where that is, right? It shouldn't look the same as the other side any longer because it's representing the solutions that you're talking about. The other thing that we have here on this particular one is it doesn't just say greater than, it says greater than or equal to. So when we have notation that has that extra equal to on the bottom, it creates for us a bracket. And our bracket or our parenthesis, whichever one we have for our problem, will always open in the direction of the shading. So for us, on this one, the bracket opens this direction because the shading is encompassed inside of the bracket. You can see if I did this, that doesn't really encompass the shading. It's sort of opening in the wrong direction. So we want our graph to open with the bracket to the right. All right, so let's back up now and fill in the middle column with the interval notation. Interval notation, I think, follows or mimics the graph so well that it's very visually pleasing. It's easy to look at and say what I have. So if I'm reading the graph, just like we always read with our English, right, and with our other kinds of two-dimensional graphs, we read from left to right. The first thing that we encounter where we have solutions is the bracket. That's the first thing we encounter. So we write this down by starting with a bracket. We write down the value at that bracket. It's an A. we put a comma. And then we have to have some sort of quantity that indicates that the bracket and the shading continue on forever. And that value is infinity. Now the reality is infinity is not really a value, it's a concept. It's the idea of increasingly larger values that never end. It's not a number. So we have to remember that we can't treat it quite like a number. It's a concept. So when we are putting anytime an infinity down, we always put a parenthesis by it. The parenthesis means I cannot equal something. And I cannot equal infinity because it's not a number I can equal. It's not a number at all. Brackets, like you see happen by the side the A here, mean I can equal something. So I had an equal to sign on the set notation. So I used a bracket to indicate that I can equal that value. Now, what happens if you start with an interval? Well, I can create a graph for an interval very much like I created the interval for the graph. So I'm going to do that first, and then we'll go back to the set notation. So we've got our number line drawn. The only value that's a number or representing a number here is the A. So again, A is the only thing I mark on my number line. And then if I'm reading again the interval from left to right, it says negative infinity, which is the values on the far left, are what's going to be shaded. So I'm shading to the left of A because it says from negative infinity all the way to A are my intervals, or is my interval. And then it tells me that at A I have a parenthesis because that's what it shows in the interval notation. So I put in a parenthesis that opens in the direction of the shading, or that ends the interval that ends at A. So that's the corresponding graph for that particular interval. In terms of the set that corresponds with, I'm making a comparison between the shading, that's what X is representing, all the numbers that are shaded, X, and the number A. And what I want to say is, where is the shading? Is the shading less than A, or is the shading greater than A? Less than. So less than is that symbol, right? And this one really is less than. It's not less than or equal to because I don't have a bracket. I have a parenthesis. So this one is X less than A as opposed to less than or equal to. My third option actually shows two numbers on my number line, an A and a B. So we'll work backwards again. The interval for that looks exactly the same. If I'm reading from left to right, the first thing I encounter is a parenthesis. That parenthesis is at the value of A. I keep trucking along until I encounter the end of the shaded red part, which is the letter B, or a number B. And at the B, I have a bracket. So that's the interval notation indicated by the shaded region. Now, the set notation for it is a little more interesting, and we will come back to the set notation later on in our lesson too. But the set notation starts at the letter A and it ends at the letter or number, whatever, B. Elisha? Not necessarily. So this A right here is simply listed as A. It still could be a positive value. It could be a negative value. It's just whatever it matches to. Right, like the only reason that you see us use, for example, like a negative infinity here is because we differentiate between going on forever in a negative direction and going on forever in a positive direction. But the A value still could be 1 or 2 and it'd be a positive number. Yeah. Okay, so the two values that are on my number line are an A and a B in that order. And the shading, which is represented by our variable X, is between them. So the X is between them. The A value is smaller or less than the value of X, and the X value is smaller or less than the value of B. And on this one, the B value is a bracket, so it has an equal to. Exactly. Do notice that the inequality brackets are always going in the same direction. You will never have a bracket that has this on one side and this on the other. Never. You could have brackets that both go like this. We'll see that happen later on. But again, the direction is still the same, right? This one's both greater than, whereas our example right now have both less than in terms of direction. All right, so what we're going to do now is we're going to actually solve some inequalities and see how this plays out with problems instead of what happened when we had equations. So our directions on number 1 and number 2 actually ask us to do basically the same thing that the chart that we just filled in did. It gives us one form and it asks us to find the other two. So I tend to go to graphs first. That's probably because I visualize things very much. I would be a visual learner. And so I tend to draw my graphs first. You can certainly do your other form first if you wish. But I'm going to do my graphs first. The number that we have in this inequality is the square root of 3. So I just put it on there. I usually just put it in the middle. Doesn't really matter. And then what I need to do is I need to shade. And I have to make a decision. How do I shade? The inequality says x is greater than or equal to square root of 3. So, Lindsay, how am I shading? To the right. I need values that are bigger than 3. Square root of 3. That's what it means to be greater than. And then somebody tell me, do I have a bracket or parenthesis? I have a bracket, absolutely. Brackets always open toward the shading, so it looks like that. And then I'm going to write my interval notation as my third item, way of expressing this. Reading the graph from left to right, I encounter a bracket. The value at the bracket is square root of 3, and I put a comma. I continue on indefinitely to the right, which means, what do I write next? Infinity is it. And then always with my infinities or negative infinities, I put parentheses to end them. All good? Okay, let's try another one. This one's given an interval notation to start with. The only number that I'm given as a value is the number 54. So I'll put a 54 on my chart, or on my number line.
Oh, no, okay. I see.
You good?
I thought because it said express all 3 forms.
Yeah, so it gives us one and we express the other two. Okay. Yes, valid. All right, this one says I start on the far left side of the graph at negative infinity, and I shade until I get to 54. So it looks like that. And then it says I have a parenthesis at 54, so it opens just like that. The graph is sort of the picture of the interval notation. And then as I'm making a comparison in set notation, the comparison has to be for x in 54, or the shading in 54. And the question is the shading less than 54? Is x less than 54? Or is the shading or x greater than 54? It's less. And is it less or less than or equal to? Just less, because it's a parenthesis. All right, any questions on those? Okay, good. So now we're going to step back just a little bit further, and we're going to start with something that's not already given to us in the solution form. We have to find the solution. We haven't solved inequalities before. That's what we're supposed to be learning in this section together. But they solve very much like equations do, with one small change. And when we encounter that change, I'll let you know. So right now, we start the same way. We see 2x plus 1 equals 6, is less than 6. And the first thing we'll do is to subtract the 1. So 2x is less than 5. And the next thing we would do is divide by 2. And so the set notation for my solution is that x is less than 5/2. The directions simply say to solve and to graph. So we have solved, and we will next graph. So here's our number line. The only value I need to put on there is 5/2. Will I shade to the left of 5/2 or to the right of 5/2? Left, because it says less than. Will I enclose the shading with a parenthesis or a bracket? A parenthesis. Now, we're done with the problem, but for the sake of your notes, so that you know what to do if you're asked, we're going to find the interval that goes with it too. Okay, so if it doesn't ask you to find the interval, you don't need to do that, but I'd like for it to be in your notes so that you can reference it if you need to later. So what is the interval that's represented by that shading? Well, it starts on the far left, which means negative infinity. We always put a parenthesis on the infinities. Where does the shading end? 5/2. And will we end with a parenthesis or a bracket? A parenthesis. So that is the corresponding solution in interval notation. It's a parenthesis because it does not have an equal to symbol. If it has an equal to symbol, it'll have a bracket. And that's true both for the graph and for the interval notation, actually. They do match. Whichever one the graph has is what the interval notation has, and vice versa. All right, let's try another one. I have 5 minus 3x over 7 is greater than or equal to 2. Absolutely. Amari's right. We're gonna get rid of that 7 to start with. We're gonna multiply both sides by 7. Please keep in mind that the whole point in multiplying by 7 is so the denominator cancels. It does not help you to distribute that 7 through the top of that fraction. It only helps you to just cancel it with the denominator, because what you're really doing is you're multiplying by 7 over 1, and you're looking across a diagonal to simplify. Okay? So in my numerator, I still have the same thing. 5 minus 3x. And it's greater than or equal to 14. Okay, again, just like the last problem, we continue to solve the way we would with an equation. We subtract a 5. So now I have negative 3x. It's greater than or equal to 9. And here's the caveat. You're right. So our next step is to divide by negative 3, right? Okay. Anytime that we multiply or divide by a negative number, the direction of the inequality changes. So this is not greater than or equal to any longer. It is less than or equal to. And I'd like to show you 2 different ways to think about why that's happening. Not because I'm going to ask you later on, why did the sign change? Because I'm not. But because I don't like the way sometimes math feels like magic. It's not magic. Right? There's a very good reason why this works. It's very simple even. So I want you to know that that's happening. So I'd like to show it to you in a inequality way, and then I want to show it to you in a numerical way. So for inequalities, let's actually go with the fact that we have negative 3x is greater than or equal to 9. I did, thank you. Yeah, there should be a negative there. Okay, so let's actually look at this, but not do any dividing or multiplying with the negative at all. So I don't want to multiply or divide by a negative. So another way that I can eliminate a negative is that I could simply add it to the other side so it becomes positive, correct? So now I'd have 0 is greater than or equal to 9 plus 3x. Okay, it's no longer negative. Okay, I can subtract by 9. So now I have negative 9 is greater than or equal to 3x. And I can divide by 3. And I have negative 3 is greater than or equal to x. But if negative 3 is greater than x, then x is less than 3. Okay? So again, right, like if I am taller than, I'm only taller than one child in my house now. That's not true. I have a daughter who's just a tiny bit taller, shorter than me. If I'm taller than my 7-year-old, then my 7-year-old is shorter than me, right? That's the way it works. It's a relationship. So while it's true, if it's true that negative 3 is greater than or equal to x, then x is less than or equal to negative 3. I flip the direction around as I rewrite it. And that's in fact, what I got here. So that's an algebraic explanation. Let me show you a numerical explanation that you will like very much. 1 is less than 3, right? Absolutely. So let's just multiply both sides by -1. How about -1 and -3? Which one's bigger? -1 is bigger than -3. So we multiplied by negative on both sides. And sure enough, when we did that, we had to change the direction of the inequalities from a number line standpoint. That's what's correct. So that's why it's happening. All right, back to our problem then. This is justification aside. We're going to do a number line. We have the only number, -3, to list on there. X is less than or equal to -3. Which direction will we shade? Left. Yep, left is less than. So it's left. Bracket or parenthesis? Bracket. Bracket always opens toward the shading and closes it in. And if I needed to write the interval notation, it doesn't ask for it, but if I did, that interval, I'll just write it up here, would be -∞ to -3 with a bracket. Any questions on that one? Okay, so direction of inequalities only changes when we multiply or divide by negatives. Doesn't change for addition, doesn't change for subtraction, doesn't change if we multiply or divide by a positive number, just negative numbers. Okay, couple extra things that feel a little bit funny, but you'll understand why they're placed here in a moment. We're going to do an example that has two inequalities with the word and between them, and then in a moment I'm going to do inequalities that have the word or between them. So if I walked in one day and I said, I am a mom and I am a teacher, the only way that statement is true is if both of those things are true. I must be a mom and I must be a teacher, or it all fails, right? Because I put the English word and between them, and it means both of them must be true at the same time. So this is what's happening here. I have two inequalities, and I want them to both be satisfied with values that work at the same time. So we're going to compare their answers when we get to the end, and then join them together to make sure that that is what's happening. So as we start, the first thing we'll do is subtract our 5. So -x is less than -1. And then what we do? Divide by -1, which changes the sign. So now it's a greater than symbol. -1 divided by -1 is 1. So that's one of our solutions. We'll come back to it and talk about a graph in a moment. Next one, we add our 5. All right, so 1 plus 5 is 6. And then we need to divide by the 0.2. What is 6 divided by 0.2? 30. Good. This is my other one. I'm going to draw two number lines just so that we can think about them, and then I'm going to draw a combined number line that's actually my solution. So these two individual number lines are not necessarily something you have to draw on your homework or anything, but if they help you, then do that. So I've got the number I've got the number 1 here, and I'm supposed to be greater than 1. Which way do I shade? To the right. I've got the number on this number line over here, 30. And I'm supposed to be less than 30. Which way do I shade? To the left. So I need numbers that match both of those shadings. So as I create a number line that has the numbers 1 and 30 on it, my first thing that I want to make sure you're aware of is you need to put them in the right order. Right? When I have just one number, I just throw it on there and I just move on. But if I have two numbers, they got to go in the right order. For example, I cannot do this. Right? It doesn't go in order that way. Yes, sir. Okay, try one more time for me.
Aren't you supposed to flip the sign?
Nope, because it wasn't negative. Yeah. It's a good catch, though, to be aware that I need to change my signs. And the only time I change signs with multiplication or division is if I've multiplied or divided by a negative. Thanks, Jonathan. Okay, so the 30 and the 1 are not in the right places, right? That's not the order of the number line. There is a natural ordering that we use all the time. There should be a 1 because it's smaller than the 30. So this is the correct ordering. So I need a number that is both bigger than 1 and smaller than 30 coming this way, and it has to be true at the same time. So I need the numbers that are trapped between. Yep. So these are the values that we're looking at. They're the trapped values. If I only have a number bigger than 1, but that it's not less than 30, I haven't satisfied the and part of this inequality. And then I look back and I use whatever symbols are in the problem. So these are both less thans and greater thans. They're not equal to, so I've got parentheses that I'm using to enclose them. And if I were to do an interval notation for it, moving from left to right, I have a parenthesis. I start at 1, I end at 30 with another parenthesis. And must be true at the same time. Okay, any questions on that one? Or is a little different. We're still going to solve them the same way, right? And we did one already, I think it was problem number 4, where, I don't know if it's actually called number 4, but it was the 4th one that we did, where we saw a denominator, and we wanted to get rid of it or eliminate it. So we'll do that here too. We're going to multiply both sides by 2. That, of course, cancels the 2 on the left with the denominator. I'm left with 4 minus x is greater than 2. So far, so good. Good. We subtract our 4. So negative x is greater than, what's 2 minus 4? Negative 2. And we divide by negative 1. So I have x on the left. I have 2 on the right. And I got to flip my sign, because this one I did divide by negative, so it's actually x is less than 2. Let's solve the other one, and then we'll talk a little bit about what the word or is doing for us. It's different. On the second one, we're going to multiply both sides by negative 3. So no matter when I multiply by a negative, I've only done it at the end so far, but here I'm doing it at the beginning, I still have to flip the sign because I multiplied by a negative. You bet. So on the right, I have negative 3. On the left, the negative 3 is canceled, leaving me with the 2x minus 7 in the numerator. Okay. Again, same process. We will add our 7. So if 2x is greater than negative 3 plus 7 is 4. If I divide by 2, x is greater than 2. I know it feels a little bit funny that these both ended up 2's. Okay? That doesn't always happen, and I'll show you an example of one later that doesn't do that. But for this one in this case, it's okay, and it will end up being just a little bit different because of that. Now, thinking about this, if I walked into the room and I said, I'm mom or I'm a teacher, that statement, because I used the word or, could be true if one or the other or both were true, right? So I walk in, both of those things are true, it's still a true statement. But if somebody walks in and only one of those things are true, it's still true for them as well. It's sort of weird. I mean, like, why would you say that? But it's true. It's correct linguistically, right? It's correct. So here, I need one or the other or both of these things to be true. So again, I'm going to sort of draw these little mini graphs just for each piece, and we'll talk about them, and then we'll combine them. You don't have to do it this way, but just so you can see it in a smaller view. The first one, put the 2's on there, says x is less than 2. Where do I shade? To the left. The second one says x is greater than 2. Where do I shade?
To the right.
And you can actually be in either one of those regions and it still be true because I've got the word or between them. Where can you not be?
Between.
Which is at 2, exactly. This one's a little weird. There's not much space between them. It's just the number 2. So I can't be actually at 2, but I can be anywhere else. So what does that look like when I combine them on a number line? Well, I only have one number to put on there, 2. I do need shading in both directions. But the intervals that I'm being given, both are less than or greater than. They don't have an equal to, right? So the parentheses will actually open in the directions of the shading, which excludes that one little spot in the middle. So how do I write this in interval notation? Because we didn't actually have one of those listed when I originally created that table. And the reason that we didn't is because it's just a combination of the others. So we have negative infinity to 2. That's what that first interval shaded looks like. We have 2 to infinity. That's what the second interval shaded looks like. You can put a comma between them if you wish. The symbol that you're supposed to be sort of technically using is a U. U means union, just the joining together of two things. So we have the interval from negative infinity to 2 and from 2 to infinity, and that's how we exclude the number 2. All right, so what's that?
What would that look like notation? Like with the two numbers?
It doesn't look like that. This is it.
Oh, that is.
This is it. This is interval notation for it. That's
Isn't
it.
there one more thing on this?
Nope.
There's like 3 times.
So it's that notation.
There's set notation. It's this right here.
Oh, okay, I got you. Okay.
I should have put my word or between it. That's the set notation for it. Yep. Okay. So this actually leads us into the last part of what we're looking at today, which is absolute value inequalities. Absolute values, remember, are distances. They're distances away from things. So if you think about a number line, and the number line here has, 0 on it, and there's a distance k away, you can go k to the right or you can go k to the left. Agreed? You can go 6 distances to the right of you, 6 distances to the left of you. We end up at positive k then on the right and negative k on the left. And this is the picture that's true for both of these that I'm going to draw so far. The difference is what we're actually trying to achieve. This says that I want the distance to be greater than k, right? You want to be further than k away, further than 6 feet away. So where are you? Well, you're out here. The second one says you want the distance to be less than or closer than the k away. So you're in here. You're in a closer proximity to the number k or than k away. Closer proximity to your value than k away. So what does that mean? Well, it means that the first one gives you a picture, this one, that looks a lot like this second problem I just did right there with the word or between it. I shaded on the outsides of something, right? And the second one has an embedded or an enclosed shading. It looks a lot like this problem, where it had an and statement, and I shaded in between two pieces instead. So what happens over here is that I get an or statement. It's possible, if you look at the right-hand side, that you are greater than k away. So x is greater than k. But if you look at the left-hand side over here, you're actually given the inequality that x is less than negative k. That's how it relates to the graph. Now, if you think about the inequality, one of your statements looks just like this one with the absolute values removed, right? Absolute value of x is greater than k, x is greater than k. The other one flips the sign from greater than to less than, and it flips the sign on k from positive to negative. So it's a double flipping of the sign to get the other inequality. And the word or goes between it. So here's your fun mnemonic device for remembering that this kind of a statement is an or statement. It's a greater than symbol. A greater than symbol always becomes an or statement that shades on the edges of things. You're over here or over here. What's that?
That's just what absolute value.
Absolute values. Exactly. You're far left or far right. Okay? The second one tells you that you're sandwiched in between. You're trapped. So on this one, visually speaking, you're between negative k on the left and positive k on the right, and you get sandwiched in a triple inequality. We saw that way back at the beginning on that chart. Remember the triple inequality? That's this one. When does that happen? Well, it happens when I have an and statement. And statements squish me between. Well, again, mnemonic device. This is a less than statement. It's an and statement. All right, so we're going to do two problems. They won't take us very long. We'll be finishing up right on time. The two problems are going to be one of each of these, obviously. So when you start in these problems that have these absolute values with inequalities, your first decision to make is it greater than or is it less than? And what does that mean? Do I have an and? Do I have an or?
Does the equal to matter whatsoever?
It just comes along for the ride. It's either there or it's not. It doesn't make any difference in how you set things up. All right, and or. Or. Start by deciding that and then deciding which of these two cases you're in. It's an or statement. So what do we do with an or statement? Well, it means I'm going to have two things written down with the word or between them. That's what it really means. One of them looks exactly like I start with lifting the absolute values off. 3 minus 2x greater than or equal to 5. The second one, the 3 minus 2x stays the same. But I double flip things. I flip the sign, now it's less than or equal to, and I flip the number. I change it from positive to negative. So I changed two types of signs. Change the inequality sign, and I changed the value from positive to negative sign, okay?
And like we said, this is only the absolute value, right?
Only absolute values do this, yep. And it has to do with measuring distances away from things.
That's when you were telling us we would never have the thing go.
Huh?
I was remembering you were telling us we would never have the thing go opposite.
Because I was saying you never read it in triple inequality.
Yeah.
But that's not what this is. This is not a triple inequality. Yep, you're right. All right, so we start with taking away a 3. That leaves me with negative 2x is greater than or equal to 2. Dividing by a negative 2, which will switch my sign. X is less than or equal to negative 1. On the other one, the steps are the same. I subtract my 3. Negative 2x is less than or equal to negative 8. Divide by negative 2. That changes my sign from less than to greater than or equal to. And I have a 4. I'm supposed to solve and I'm supposed to graph. This is the solution. Must have the word or between it. The graph needs to have the numbers 1 and 4 on it, and they need to be in order, which means 1 first, 4 second. It's an or statement. It's going to shade on the edges. But if you don't remember that, you should be able to see it from the inequalities as well. Where is x less than, I'm sorry, that should have said a -1. Where is x less than -1? Well, to the left. So I shade to the left. Where is x greater than 4? Well, I shade to the right. These do say greater than or equal to, so do I have parentheses or brackets? I have brackets. And while it doesn't ask it, let's go ahead and write it just for your notes' sake. What does this interval look like? Well, it's -infinity to -1 with a bracket on the -1, union, bracket on the 4 to infinity. Any questions on that one? One more. Obviously, I know it's an and statement because I told you I was doing one of both. But you should know it because it's a less than statement. This is an and. With an and statement, you don't set up two inequalities with the word and between them. You set up a triple inequality. So, what does it look like? Well, half of it looks exactly like it already looks. 6 minus 4x less than 2. Again, just remove the absolute values, pretend like they weren't there. The other half comes before it. That's the triple part. And it's the opposite sign, -2. We solve a triple inequality the same way we solve an equation. We just have 3 pieces to do, 3 parts or 3 sides to it. So when I subtract my 6, I have to subtract the 6 in all 3 locations, or on all 3 sides. -2 minus 6 is -8, is less than -4x, is less than -4. I'm trying to get x alone, so I'll divide by -4. Dividing by a negative changes the direction of the signs. Do you see how they're still opening in the same direction, like comparatively to one another? They switched, but they both switched. Yeah. -8 divided by -4 is 2. -4 divided by -4 is 1. You can totally leave it written like this. If that bothers you, you could also change it to be written like this. Doesn't matter. The graph has a 1 and a 2. Whether you write it the first way or the second way, the 1 and the 2 have to be in the proper order. You're sandwiching. It's an and statement. The value lies between, and this one has parentheses. So the interval notation, if you were asked, is 1 to 2. Any questions?